Okay, so now let's look at section B, B9, the story of matches. Okay, basically the important part here, right, is just this person discovered that upon heating white phosphorus or exposing it to sunlight, it will turn into another form, which is your red phosphorus. So this form of element is non-toxic as compared to white phosphorus, which is toxic. Okay, so here they show you the structure of red phosphorus and white phosphorus. So now let's look. Okay, when the match is struck against the striking surface of the matchbox, this is the equation that has taken place. This is the chemical equation. Okay, so now let's look at part A. Part A says, using oxidation state, explain whether the reaction involving your potassium chlorate and phosphorus is a redox reaction. First thing, what is the meaning of redox reaction? Basically, it is when oxidation and reduction occurs simultaneously at the same time. Okay, so now let's look at the equation again. Okay, first let's look at the oxidation state of chlorine in KClO3. So for those who are not sure how to calculate the oxidation state, right, we do it together. So KClO3. Okay, let's look at oxygen first. Oxygen has the oxidation state of -2, correct? And then because there's 3 of it, so I times 3 to get -6. Potassium is in group 1, so it forms the oxidation state of +1. Correct? So +1 and -6, how do I balance out the charges such that the overall charge is 0? It means that my chloride ion, right, must have a oxidation state of +5, correct? In order for all the charges to be balanced out. Okay? So Cl will be +5. Okay, then now let's look at the product. KCl, what is the oxidation state of chloride ion again? Same thing, the oxidation state of potassium is +1. So it means that my chloride ion must have an oxidation state of -1. So what has happened here? It has been reduced. Correct? Why? Because there has been a decrease in oxidation state from +5 to -1. Okay? So now let's look at P, phosphorus. What's the oxidation state of phosphorus in the element form? It is 0. Correct? Then now in the product P2O5, same thing. I want to calculate the oxidation state of phosphorus. So the oxidation state of oxygen is -2, correct? Then because there's 5 of it, so I times 5, I have -10. Okay, so in order to balance it, right, here must be +10, correct? So that my overall charge is 0. And then now take a look at how many phosphorus ions are there? There's 2 of it. So for each phosphorus ion, right, there's an oxidation state of +5. Correct? Phosphorus atom, sorry, not ion. Okay? So here the oxidation state will be +5. Okay? So what has happened here? Oxidation has occurred because there's been an increase in oxidation state of phosphorus from 0 to +5. Can? Okay, so how we explain, right? We have to say that first we talk about the oxidation, which is phosphorus, correct? So we say that phosphorus has undergone oxidation as the oxidation state of phosphorus has increased from 0 in P to +5 in P2O5. Correct? Okay, so I'm done with the oxidation part. Now my reduction. So what has been reduced? My chlorine. So chlorine has been reduce as the oxidation state of chlorine in as the oxidation state of chlorine has decreased from +5 in KClO3 to -1 in KCl. Correct? So therefore there has been a reduction. So therefore there has been a reduction because there is oxidation and reduction. Okay? So now part B. The phosphorus oxide P2O5 that is formed in the reaction of striking a matchstick absorbs water from the air to form HPO3. Write a balanced chemical equation for this reaction. Okay, so this will just be P2O5, correct, plus water to form HPO3. Then is it balanced? It's not balanced, so I must balance it. So here will be 2. Yeah, this is the balanced chemical equation. Okay, then now part 2. On addition of more water, phosphorus acid, which is H3PO4, is formed. Explain with the aid of an ionic equation why a solution of 1 mole per dm cube of phosphoric acid can produce a much higher concentration of H plus ions as compared to HPO3. Okay, so here, right, how we explain is we say that, okay, first let's talk about phosphoric acid, H3PO4, sorry. H3PO4 will ionize to form 3 moles of H plus and PO4 3 minus, correct? Whereas for HPO3, you give me 1 mole of H plus and PO3 minus, correct? So why would it give me a much higher concentration of H plus? How do we explain this? We need to talk about this term called tribasic. So we say that H3PO4 is a tribasic acid. So what does tribasic means, right? It means that for every, it means 1 mole of acid will produce 3 moles of H plus ions. Okay? So 1 mole of acid will produce 3 moles of H plus ions to be neutralized in water. So the ionic equation would be H3PO4 equals to form 3H plus and PO4 3 minus. Okay? Okay? So this is the ionic equation. Okay, then now part C. Based on the diagrams of red phosphorus and white phosphorus, compare and contrast the structures of red and white phosphorus. So let's look at the structures. Okay, so these are the structures. What is the similarity and what is the difference? Let's talk about it here. Okay, first let's talk about the similarities. Okay, your phosphorus. Let's look at red phosphorus first. Each phosphorus atom is covalently bonded to how many P atoms? For red and white phosphorus, right, it is covalently bonded to 3 other phosphorus atoms. Same thing for red. Correct? So that's the similarity. We can say that both red and white phosphorus consists of phosphorus atoms that are covalently bonded to each other. Or if you want to be more detailed, right, you can say that each phosphorus atom is covalently bonded to 3 other phosphorus atoms. Can? I'll prefer this answer because it's more detailed. So now that we've talked about similarities, let's talk about the differences now. So for the differences, okay, look at red phosphorus. It is a long chain molecule, correct? They are all linked together. As compared to your white phosphorus, they are all separate molecules. Okay, so that's one of your differences. What you can say is, for your red phosphorus, it exists as a long chain or giant molecule, whereas for your white phosphorus, okay, they exist as simple molecules in a tetrahedral structure. Okay. Okay, now for part D, based on the structures of phosphorus sesquisulfide and antimony sulfide, state the empirical formula of antimony sulfide. What is empirical formula? It is my simplest ratio. Correct? So let's look at the structure. Okay, so this is my two structure. Let's look at antimony sulfide. How many sulfur atoms are there? Let's see. Okay, sulfur I have, my antimony. How many antimony atoms are there? 1, 2, 3, 4. Correct? Then now sulfur. I have 1, 2, 3, 4, 5, 6. Okay, so Sb4S6. How do I make it to form the empirical formula, the simplest ratio? Can it be simplified further? Yes, right? So it will be Sb2S3. Correct? So this is my simplest form. It cannot be simplified further. So this will be my empirical formula. Okay? So the answer would be Sb this will be my empirical formula. Okay, then now for part 2, they say predict 2 physical properties that are similar for both compounds. Okay, so for phosphorus sesquisulfide and antimony sulfide, what's the similarity between their compounds? They are both simple covalent compounds, correct? How do I know it? Look at phosphorus sesquisulfide. It is made up of phosphorus and sulfur atoms. Both of them are non-metals. So non-metal plus non-metal, it will be a simple covalent compound. Okay. So what are the physical properties of simple covalent compound? First point, you can say they have low melting and boiling point. So this is a chem bonding question. Okay. So same thing, we use the SAE structure. So first one for S, I say that they have simple molecular structures. Okay, so next one is the attraction. They have, okay, there are weak intermolecular forces of attraction between molecules. Okay, last one, E stands for energy. Therefore, only a small amount of energy is required to overcome the forces of attraction. Okay, then the second physical property that you can talk about is they are poor conductors of electricity. Why? Okay, because they are made up of simple discrete molecules that are neutral and uncharged. So they are unable to act as mobile charge carriers to conduct electricity. Okay, so this is a keyword. There are no mobile charge carriers available to conduct electricity. Okay, so let's work on the electrolyte first. I have Cs plus, H plus, Cl minus and OH minus. Okay, first let's talk about the cathode. In the electrolytic setup, your cathode is my negative electrode, correct? So it will attract positive ions. Okay, so Cs plus and H plus, which will be preferentially discharged? It is H plus, correct? So what would the half equation be? It will be 2H plus 2 electron to give me hydrogen gas. Okay, so this is the half equation for my cathode. Then now let's look at the anode. Anode is my positive electrode. So it will attract my negative ions. Okay, then I have Cl minus and OH minus. Which one is preferentially discharged? Okay, the keyword here, right, is this, concentrated. So when you talk about concentrated, right, my Cl minus will be the one that is preferentially discharged. Okay, so if I write the half equation, it will be 2Cl minus to form Cl2 chlorine gas plus 2 electron. This is my half equation. Okay, so I want to determine whether electrode 2 is the anode or cathode. Let's look at electrode 2. The hint is in the question. It says there's a colored gas observed at electrode 2. So now based on our half equations, 2H plus 2 electron to form H2 and Cl2. Which one is the colored gas? It is my chlorine, correct? This is my pale greenish yellow gas. This is my colored gas. So it means that this is electrode 2. Okay? So say that electrode 2 is the anode. Okay? So the half equation is just 2Cl minus from Cl2 plus 2 electron. Okay? Then for part B, describe the observations at electrode 1. So I know that this will be the half equation at electrode 1. Correct? My cathode. So what would the observation be? What is being produced? It is my hydrogen gas. Okay, so the observation, I have to first say that electrode 1 is the cathode. So I can also write down the half equation. From H2 hydrogen gas. So when they talk about observation, you can say that there is effervescence of a colorless gas, which is my hydrogen gas. Okay, Okay, then now for part C, this is state and explain the observations made on the electrolyte in diagram A as experiment proceeds. Okay, now let's look at the experiment. Okay, the keyword is here, this part. So as the experiment proceeds, my H plus is being preferentially discharged. Correct? So what does this mean about the concentration of H plus ions? It will be lower than the concentration of OH minus, correct? So how do I explain? So you can see that, okay, we are going to use the color of the universal indicator to help us explain the observation. Remember at the start they said a few drops of universal indicator was added to cesium chloride solution, which is a salt solution, correct? This is a salt. So salts are neutral. They have a pH of 7. So what's the color of universal indicator in neutral solution? So you can see that universal indicator has changed color from green to what color? Purple or blue? Okay. So this green is for neutral solution. Purple and blue indicates an alkaline solution. Why? Because as experiment proceeds, your H plus ions are preferentially discharged at the cathode. So the concentration of H plus ions is less than the concentration of OH minus ions. Therefore, solution turns alkaline. Okay, that's why your universal indicator will turn purple or blue. Okay, so I know that my positive electrode which is my cathode, is copper. Okay? Then, let's do the question. It says write the half equation for the reaction at the copper metal, which is my cathode. So, the cathode, being my positive electrode, it will attract the positive ions. Correct? So, based on what I have in the electrolyte, the ions available in the electrolyte, which are my positive ions? It is this, Cu2 plus and H plus, correct? And which one will be preferentially discharged? It will be Cu2 plus because it is lower in the reactivity series than hydrogen. So, the half equation would be Cu2 plus 2 electron to form copper solid. Okay? So this is the half equation for the reaction at the copper metal. So remember that at the cathode, right, it is always reduction. And at the anode is the oxidation. So Cu2 plus has been reduced to form copper solid. Okay, then for part E, suggest a way to increase the voltage of the electric cell. Okay, how do we increase? We can use two different metals. With a greater difference in reactivity. Or you can also say we can use metals that are further apart in the reactivity series. Okay. Then for part F, if the position of zinc and copper electrodes in diagram B were switched with each other, what will be observed instead in the setup of diagram A? So, zinc and copper is switched. Okay, zinc is my anode, correct? Because it's more reactive, so the more reactive metal will be my anode. Then copper is cathode. Okay, so So right now, right, can you see that my zinc is actually linked to my cathode, correct? Anode and cathode. Whereas for my copper, it is linked to the anode. Okay, so anode, cathode, cathode, anode. Okay, so if we switch over now, so I have, okay, so initially, in this setup, zinc, okay, is linked to electrode 1, correct? Whereas copper is linked to electrode 2. Okay, recall that the question says a colored gas was observed at electrode 2, which is here. So there will be a colored gas. Okay, then electrode 1 is the cathode, and here is my anode. So now if I switch the positions around such that it is Cu and zinc now, correct? If I switch it over, your cathode, your electrode 1 and your electrode 2, they will switch over also. So electrode 1 will now be your anode and electrode 2 will be your cathode, correct? So recall that the colored gas was produced at the anode. So now when copper and zinc have switched over, right, your colored gas would be at the electrode 1 now instead of electrode 2. Okay? So the answer would be, there will be a pale greenish gas. Can say pale green or colored gas, which is my chlorine gas, will be observed at electrode 1 instead of electrode 2. Okay? Okay, so now for B11, an analysis of the melting points of the elements of period 2 and their oxides was done, and the information is recorded. So this is graph 10.1. They are telling you about the melting point of elements. Whereas for graph 10.2, it is telling you the melting point of the oxides of elements. So for part A, using information in graph 10.1 and 10.2, describe the trend in melting points across period 2. So let's look at graph 10.1 first. What is the general trend for elements in period 2? From lithium to carbon, there's a general increase in melting point, correct? But look at from nitrogen to neon, there's a sharp decrease followed by constant temperature. Constant melting point, sorry. So we write that down first. So from graph 10.1, right? Across the period, your melting point increases steadily but decreases sharply after carbon, correct? Okay, then all the elements after carbon have a constant low melting point. Make sense? Okay, they all have a constant low melting point. So that's from graph 1. Okay, then now, from graph 10.2, what is the trend? Let's look at graph 10.2. Okay, what is the general trend of the melting point? Across the period 2, right, there is a general decrease in melting point, correct? Except for this beryllium oxide, it is your anomaly. Okay, So again, first you write the general trend. So melting point of oxides generally decreases across the period except for beryllium oxide, which has a higher melting point than lithium oxide. Okay, so this is how you answer this question. Then now for part B, name the elements in period 2 which are solids at room temperature. So room temperature, I'm talking about 25 degrees Celsius, correct? So now let's look at the elements. Let's look at graph 10.1. Okay, if you notice, right, from nitrogen to neon, it has a low melting point, which is about, this would be about 25 degrees. Okay, so let's assume it's at room temperature. Okay, what is melting? Melting, there is a change in state from solid to liquid, correct? So from nitrogen to neon, with a low melting point of, let's say, 25 degrees Celsius, at room temperature, they would be in the liquid state, correct? Because they have already melted. Then, for lithium to carbon, they have a melting point that is higher than 30 degrees Celsius. So this means that at room temperature, which is 25 degrees, they would still remain in the solid state. They wouldn't have melted yet, correct? So how do I answer? The answer would be, those that's in the solid state would be your lithium, beryllium, boron, and carbon. Can? Okay, for part C, the form of carbon in graph 10.1 is a good conductor of electricity. State the name of this form of carbon and with reference to its structure, explain why it is a good electrical conductor. Okay, this one from graph 10.1, carbon. The melting point is 3000, correct? So it has a very high melting point. Okay, so when it comes to carbon, right, and it has such a high melting point, what do you immediately link it to? You have to immediately link it to your giant covalent structure. Remember, your giant covalent structure has an extremely high melting and boiling point. So, for giant covalent structure, the ones that you all have learned would be diamond, graphite, mainly these two, correct? And some others. Okay, so with this in mind, they say it is a good conductor of electricity. So, diamond versus graphite, which one is a good conductor of electricity? The answer is graphite, correct? So, what is this form of carbon? It will be graphite. Okay? So, with reference to its structure, this is a bonding question. Okay, your chem bonding. So, remember, okay, first, in order to be a good electrical conductor, you need to have two factors. First, there must be presence of mobile charge carriers. It must satisfy these two conditions in order to conduct electricity. Okay, so how does graphite fulfill these two conditions? You can say, that graphite has a giant covalent structure. I'm just going to write in point form, okay? So, each carbon atom is covalently bonded to 3 other carbon atoms in a hexagonal plane arrangement. Okay, all this is directly from your chem bonding notes, so just refer to your notes. Okay, then since each carbon atom has 4 valence electrons, correct? Because carbon is in group 4, so it has 4 valence electrons, and only 3 of it are used for bonding. It means that each carbon atom has 1 available electron to act as, the keyword is mobile charge carriers, in order to conduct electricity. Okay? Okay, then now for part D. Explain the difference in melting point between your lithium oxide and beryllium oxide. Okay. This is a very standard bonding question. So first, let's determine what type of bonding is present. Lithium oxide and beryllium oxide. I have a metal and non-metal, correct? Lithium is a group 1 metal, beryllium is a group 2 metal, and I have a non-metal, oxygen. Okay, so metal and non-metal, what bonding is this? This is my ionic bonding. So both are ionic compounds. How do I compare the melting point? So again, from the graph, right? So now let's look at the graph 10.2. Lithium oxide and beryllium oxide. Beryllium oxide has a higher melting point as compared to lithium oxide. So first we state that beryllium oxide has a higher melting point than lithium oxide. Correct? So because they say explain the difference, they didn't tell you whether they did not tell you which one has a higher melting point, so you got to state it in your answer. Okay? Then now once you have answered the trend, you need to explain. So how you explain? Okay, first, lithium oxide is made out of lithium plus and O2 minus. Correct? What is the charge difference? The charge difference, right, is 1 times 2. Okay? So this is the charge difference. Then now let's compare for beryllium oxide. BeO. I have Be 2 plus and O2 minus. What is the charge difference? It is 2 times 2 equals to 4. Which one has a higher charge difference? It is my beryllium oxide, correct? So this one has a higher charge difference. So higher charge difference. Okay, wait. Okay, so I erase this. So once you understand this concept, how do I phrase it? Would be, you have to say that, okay, first you say that both beryllium and lithium oxide, they are ionic compounds. So how do I compare between ionic compounds? I compare the charge difference. Okay, then you say BeO has a larger charge difference. Okay, so what does a larger charge difference indicate? It indicates a stronger electrostatic forces of attraction between your oppositely charged ions okay, then how I need to link it to melting point. So how do I link it? I say, therefore, a larger amount of energy is required to overcome the stronger forces of attraction. this is how you answer this question. Then now, remember for, okay, this one, right, is just a supplement. For ionic compounds, if both compounds, they are ionic, right? How do I compare them? I compare by the charge difference. Okay. Then for simple covalent compounds, if both are simple covalent compounds and one has a higher melting point, how do I compare? I use the MR to compare. Okay, so this is the difference. Ionic compound and simple covalent. For ionic compounds, I use charge difference. For simple covalent compound, I use the MR. Okay? Then now, for part E, explain why the oxide of neon was not included in the graph 10.2. Okay. So let's write 10.2 again. 10.2. I have, okay, the oxide of neon is not even included. Why? Remember, neon is in group 0, correct? So what's so special about group 0 elements? It is a noble gas, correct? It's a noble gas. It is inert / unreactive. This is the unique property about noble gases, correct? So because it is so inert or unreactive, it will not react with, it will not even react with oxygen to form an oxide. Okay? Okay, so now for B11, glutathione is a substance found in every cell in the body where it acts as an antioxidant to neutralize your free radicals and blah blah. Okay, so the important thing is, this is the structure for glutathione. Okay, so part A, name and draw the linkage that is found in this. So let's look. What is the linkage present? This is, what linkage is this? This is your amide linkage, correct? So, how does your amide linkage look like? Okay, and how is your amide linkage formed? It is formed from diamine and dicarboxylic acids. Okay, you must be very familiar with how your amide linkage and your ester linkage, how does it look like? Okay, these two are the most common linkages that they will test on. Okay, so part B, draw the structures of the 3 amino acids used to make it. Okay, now let's look. Okay, I have 2 amide linkages here, correct? So if I split into 3 amino acids, how will I split? So it will be this, one of it, and here would be my carboxylic acid, correct? Remember my dicarboxylic acid. Then my second monomer would be this, correct? Do you all get the idea of how to do this now? Okay, the third one would be this stretch. Okay, so these 3 monomers, when they react together, it undergoes condensation polymerization to form your amide linkages. Can? Okay, so drawing the structure, it will be H. this is the first one, which comes from here. Remember, I must add in the OH to form the carboxylic group. Okay. Then now my second monomer, my second amino acid, would be N. This is my amine. CH. Then carboxylic acid group. Okay, so this is my second amino acid. My third amino acid would be same thing, my amine. Okay, so this is my 3 amino acids. Okay, so now for part C, it was found that a person with HIV has only 5 times 10 to the power minus 6 moles of glutathione in 5 cm³ of the blood sample. They want you to calculate what is the concentration in terms of gram per dm³ in the blood. Okay, so how do we work this out, right? From the question, it says that in 5 cm³ of blood, there is 5 times 10 to the power minus 6 moles, correct? Okay, then now look at the units for concentration. We are working backwards in this case. Gram per dm³, meaning what they want you to find, right, is in 1 dm³ of blood, what is the mass in terms of gram? Okay, so we work backwards. We find the number of moles in 1 dm³ of blood. Okay, so in 1 dm³ is 1000 cm³, correct? So in 1 dm³ of your blood sample, what's the number of moles? I times 200. So same thing for the right hand side also, times 200. So 5 times 10 to the power minus 6 times 200, the answer would be 0.001 mole. Okay, so now I have the number of moles. How do I find the mass? I'm going to use this formula whereby number of moles equals to the mass over mR. I know what is the number of moles. Do I know what is the mR? I can find the mR, right, from the structure. Correct? So if I condense all this, it is actually C10H17O6N3S. Okay? So to find the mR, my mR will be 307 gram per mole. Okay? Then now, I find the mass. So the mass is equals to 0.001 mole times 307 gram per mole. This is my mR. To find the mass, which is 0.307 gram. Okay? So it means that in 1 dm³ of blood, the mass would be 0.307 gram. So the concentration in terms of gram per dm³ would thus be 0.307 gram per dm³. Understand? So in this case, you are going to work backwards. Okay? Okay, then now for part E, the last question. Name a synthetic polymer that has the same linkage found in glutathione. Okay, what is this linkage? This is my amide linkage. Correct? So, one example, this one is from your notes, would be nylon. Okay, and what is the structure? Showing 2 repeat units. It is, and this one is straight from the notes. So just refer to the notes for this. So this is the structure. Remember, you must show 2 repeat units. Okay?